going to start easy for the people who are not expert in the field and gradually go into the details of how near ignition was achieved on the National Ignition Facility. Okay, so so fusion ignition combines. Sorry, I have to deal with my screen. Combines light hydrogen atoms. Sorry. It's just, I don't see my slide. Oh, okay. Combines lines nuclei into a heavier nucleus and release huge amount of energy. So basically, what you want to achieve is the fusion of isotopes of hydrogen, deuterium and tritiums, and the fusion of hydrogen and deuterium will release a medium-4, which is the alpha particle that we call, and a neutron. The difference in mass between the deuterium tritium, the initial nuclei, and the resulting nuclei comes into energy, into kinetic energy. Kinetic energy into the alpha particle. For the alpha particle, the kinetic energy is about 3.5 MeV, and a neutron, which kinetic energy is 14.1 MeV. So the energy released by the fusion of those small nuclei is huge, and that's the energy you're going to collect. You're trying to collect to create to make to make electricity. Okay, but fusion is not easy. And why is it not easy? Because the Coulomb barrier makes high temperature necessary for DT thermonuclear fusion to happen. So what happened is those two nuclei of deuterium tritium, they don't want fusion because of the Coulomb barrier. So you need high enough temperature in your plasma to overcome that barrier. And if you look at the fusion rate, so on the right side, there is a plot of fusion rate versus temperature for various fusion reaction. You have DT. DT is the highest one. That's why DT was big.
You can close it.
And what you can see is that the DT fusion reaction peaked at about 63 keV. Obviously, we cannot reach 633 keV on a laser because of mostly radiative loss that would be too large to reach that kind of temperature. So typically, you're aiming to a 5 to 6 keV initial temperature to trigger the DT reaction. But here, what you can see is the yield. So yield is a function of density of deuterium tritium. It's the NINJ, the reactivity times the volume times the time. So you can clearly see that you also need high enough density to make enough yield and confinement for a long enough time. So there are actually 3 ways to make fusion. The first one is the natural one, which is the sun. So in the sun, the confinement is due to gravity. But here the density is really high. It's 10,000 times the solid density. But the temperature is pretty low, around, on a fusion scale, is about 1 keV. But the confinement time is huge, 10 to the 5 years. In magnetic confinement, the density is pretty low because you're talking about a gas, so is much lower than the solid density. But the temperature is much higher. Here we talk about 10 keV, and the confinement time we're talking about seconds, and that's the challenge to reach high enough confinement time to have enough neutrons. In inertial confinement fusion, the density is really high because you're compressing the solid. I explain you later how. So you want to reach 1,000 times solid density at a temperature of 10 keV, which is about the same as the magnetic confinement, but the confinement time is much lower. We are talking about tens of picoseconds. But because of the high density, then you can have high yield. So the idea of inertial confinement fusion is to compress the fuel to thermonuclear conditions. So in ICF, you start with a cathode that is an ablator. It's typically a low-Z ablator made of plastics, or you will see high-density carbon. And then there is inside there is the deuterium tritium fuel, which is at cryogenic temperature. There is a layer of cryogenic deuterium tritium, and inside there is a gas of deuterium tritium. And you start with a radius of about 1 millimeter, and a density of the density of the cryodity is about 0.25 gram per cubic centimeter, and the density of the gas inside the cryogenic layer is about 0.03 gram per, no, the rho, sorry, it's the density times the radius, which is about 0.03 gram per square centimeter. Now you want to make this converge by about 35 times. So you want to reach a diameter which is going to be about 60 microns. And here the density will jump to something like 700 gram per cubic centimeter, and a rho about 3 gram per cubic centimeter. Why do you want to reach that high of a density? Because you want to stop the alpha. So you remember in the fusion reaction, you make a neutron at 14.1 MeV and an alpha particle at 3.5 MeV. And fusion works if the alpha particle is going to eat up the fuel and start the chain reaction. And for the alpha to release its kinetic energy into thermal energy into the hotspot, you need high enough density collision so that it stops into the hotspot and heat up the hotspots. So to make that, the most efficient compression is spherical. So remember, if you try to compress a thin slab of matter with a laser, basically the Rankine Union equation is going to tell you that you can only compress it 4 times, which is not enough to reach the density we want to reach. So if you want to reach much higher density, then you will use a sphere, because the theory on sphere is you can compress it 33 times. It's just the geometrical effect. So you can reach much higher density with a sphere than with a slab. And you want to use a hollow shell. And the hollow shell, you want to use a hollow shell because it's easier to compress. So you want to reach really high velocities, implosion velocity. I'll show you what later. And if you wanted to compress a 1 millimeter ball of deuterium tritium at velocities that are relevant for ignition, you need a 500 megajoule laser, which we don't have. So if you want to reach the velocity that you need for ignition, you need the shell. Then you can reach the velocity that you're gonna need. And why do you need velocity? Because where you make kinetic energy, and that compression, that kinetic energy is going to transform into thermal energy and it's going to heat up the hotspot. And to compress it, the most efficient compression is isentropic. Why that? Because if you just launch a huge shock to compress your capsule, you're gonna create entropy. And if you create entropy, you maximize the work you're gonna need to compress your capsule. But to minimize the entropy and to facilitate the compression, then you need to compress on an adiabatic compression. It's hard to do experimentally. So what has been done over the years is not a ramp compression, which would be the isentropic compression, but you're launching a series of shock. I'll show you later, because just experimentally it's easier to do. And as I said, the mass compression is fast, and that's why you use that shell, that hollow shell. So here, what you can see on the red is the hotspot compression that you want to reach. So here you have temperature and density. The black curve is is the density, and the red curve is temperature. So you want to reach high temperature in the center. If it ignites, it goes up to 12 keV in the hot spot, but then it's cold on the outside. So the piston, the capsule is cold and the hot spot is really hot. So you go from 12 keV in the center to a few hundred on EV in the ablator. And so what kind of velocity do you need? Well, if you look at those equations, you have the kinetic energy, which is the mass of the fuel times the velocity of the implosion. And if you want to have a margin, which would be twice the energy in the fuel, well, you can see that you need something like 360 kilometers per second. Just to set the stage, when a rocket ship goes into space, the velocity is about 14 kilometers per second. So this is really fast, and it happens in a few nanoseconds. So typically the pulse are between 10 and 20 nanoseconds on lasers. And you're going to reach really high aberration pressure. So we are talking about hundreds of megabars in radiation pressure. Yeah. So as I said, at Livermore, where I used to work, we only focused on indirect drive, confinement fusion. I will go later into the various schemes that you can have. So what do you need to achieve inertial confinement fusion? Well, you need a huge laser. The huge laser we're talking about is the National Ignition Facility. Here you use 600 megajoule of electricity, and you generate about 1.8 megajoule of laser at 480 terawatts. The laser is composed, I'll show you. So here is a small movie of what's going on. So this is the control, this is the National Ignition Facility control room. It's been designed on the model used for the launch of the Cap Canaveral, the rocket ship. So here you make the laser. So here you have the pilot, and you're stacking 88 picosecond Gaussian pulses to form a larger pulse, which is going to be up to 20 nanoseconds long, depending on what ablator you're using. Then you have 192 beams, and the laser pulse is going to travel within the amplifier, going from a millijoule in the pilot to 1.8 megajoule, 2.2 megajoule in the chamber. The beams are rectangular. They are all rectangular. They are all going into a 10-meter chamber, which is at the center of the building. The building is like 3 football stadiums roughly, and the beam are dispatched into 3 cones. It's called polar drive because I'll show you later. You want those beams to go into a small cylinder made of gold or depleted uranium, and that's the best geometry to do it. So you have the 192 neat beams going into what we call a hohlraum. This is creating a bath of X-rays with a radiative temperature of between 200 300 EV, and that's compressing your capsule. The capsule is compressing in something like 5, if it's diamond, it's like 5 nanoseconds, 5 to 6 nanoseconds, and then you make your neutrons. So that's, that's how it works. Now, if you want to look at images, just for you to realize what we're talking about, this is a target that we use on NIF. So remember, the target is cryogenic. The initial temperature of the target is 18.6 Kelvin. So you need to shield the target from all heating sources inside the target chamber. So the target, which is that thing, the hohlraum here in the middle, is within a shroud that is protecting it from all heating sources. And the shroud that that big thing, the gold thing that you see is going to open 6 seconds before the shot. Here, if you have a closer look at the hohlraum, it's about 1 centimeter in length and a few millimeters, 6 millimeter diameter. And it's made either of gold or depleted uranium. And here you can see also all the wires that are required to cool down the hohlraum and the field tube, which is important. I'll talk about that later, which is bringing the DT fuel into the capsule. You do that right before the shot. Well, a few days before the shot. And here you have a picture of the capsule. The capsule is laying in the equatorial plane of the hohlraum. And to hang the capsule, you have two small, really thin 40 nanometers film of plastics that are holding the capsule in the center of the hohlraum. So just to give you an idea of what we're talking about. Okay, how does that work? So now you have your 1.9 megajoule of lasers that are coming into the hohlraum. And they are what you want to do is have them make a bath of X-rays that are going to ablate the capsule, and then you have a rocket. So you have matter expanding and launching a shock that is converging. And the goal is to reach a really spherical shock, spherical compression. But it's complicated because it's a dynamic system. So you can see the laser, you have the outer beams, the inner beams, and you can see that you are ablating. This is a hydro simulation. You are ablating the capsule and you are ablating the wall. Everything is moving at the same time, where the laser beams are pointing is moving and the capsule is moving at the same time. And what you can see here on the plot is in blue, it's the typical pulse shape, which is used for a diamond capsule. So here you have 8 nanosecond pulse shape. And it goes up to, this one goes up to 450 terawatt. It's about 1.6 megajoule, I think. And you're reaching a radiative temperature of about 280 electron volt. So here the challenge is really to reach a spherical compression. That's the difficulty. So now you have 1.3 megajoule of X-rays, and you have a 1 millimeter radius capsule into your hohlraum, which means you're only coupling 150 kilojoule into your capsule, okay? And now the challenge is going to be, you want to compress that 2 millimeter capsule into a 50 micron hotspot. And here you have another challenge. So now you have 20 kilojoule of kinetic energy that is going to be reached at peak velocity. And now here's the new challenge is this one, hydro instabilities. The capsule is going really fast, as I told you, 450 kilometers per second. It's really thin. It gets thinner and thinner because the capsule is ablated by the X-rays. And what can happen if you have any homogeneity of the drive or of the density, you can trigger hydro instabilities, related to Richtmeier-Markov instabilities. Why it matters? Because, come back. Because the blue part is really hot here, but the purple part is really cold. When I was mentioning keV in the blue part, hundreds of eV in the pink part, which means if you have instabilities, you're launching ice cubes into your hotspots, and ice cubes are going to cool down your hotspots and prevent the burn wave from reaching the DT and achieving ignition. So hydro instabilities are a major issue and have to be controlled if you want to reach ignition. Okay, so the ignition campaign started in 2009, and that was called NIC. And here, so the ignition facility the National Ignition Campaign, sorry, started 3 years. lasted 3 years from 2009 to 2012. And in terms of yield production, it was not as successful as planned, obviously, because the National Ignition campaign was really ambitious in what it wanted to achieve. It went with the highest compression possible, with plastic capsule, really long pulses. So a lot of laser plasma interaction issues, a lot of hydro instabilities issues, and a lot of symmetry, how well you control the symmetry of that capsule coming in. So it was really successful in bringing up to speed the many diagnostics that you need to understand your implosions. And that was an amazing achievement, but in terms of neutron, not so much. So, but all those diagnostics allowed us to understand what was wrong in the implosion, and it was quickly realized that hydro instabilities, mix was the issue. So here you can see a 3D simulation of what your hotspot looks like, and you see all those spikes that you can see here. They're going to cool down the hotspot and prevent and lower the temperature, so lower the reactivity and prevent ignition to be achieved. So so one way to stabilize hydro instabilities is to increase the adiabat. So you don't converge as much. So initially you want to converge 35 times. So when the adiabat is higher, then it's harder to compress with the same amount of energy. And your hotspot is going to be larger, which means if it's larger, it's less sensitive to all those little spokes, cold spokes that are going to plague your hotspot. So that's what was called the high foot campaign, which started somewhere in 12 and lasted up to 15, 16, a little bit. And that was successful in lowering hydro instabilities and achieving higher gain. So the yield was actually multiplied by about 25 here. So on the right, you see years and yield, and on the hotspot, you see what is important, which is the energy into the hotspot and the pressure. And the pressure is telling you how well your piston is compressing your hotspot. So that's an important measure. The pressure is obviously not measured, it's inferred from experimental observation like temperature, density, things like that. So that's the high foot campaign, quite successful at improving stability, hydro stability, but at some point it leveled off. We couldn't go higher. So then we had the HDC campaign, which is the high density carbon. So far we had used plastic ablators. So the capsule was 2 millimeter in diameter, and the ablator was about 180 to 200 microns thick. Why it matters? Because at a constant velocity of the shock, the pulse shape is set by the time the shock will take to transit into the ablator. So if you can use a thinner ablator, your pulse shape can be shorter, and you can reduce laser plasma instabilities into the hohlraum, and you're going to gain on that. So diamond is 3.43. So the density of diamond is about 3.45. The density of CH is about 1. So for the same ROR, you can go to the much thinner ablator. So you can go from 180 to about 80 micron, which means you can use a much shorter pulse shape from 15 ns to 8 ns, which means that, okay, so in the hohlraum, you use gas. The hohlraum, which is that cylinder of high Z, you need to put gas in it to prevent the wall being ablated by the laser to totally fill the cylinder and prevent the laser from going in. And the issue with gas is it's gonna be the cause of laser plasma interaction, like Raman, stimulated Raman. And what it does, it's basically you have light that is not coupling, that is reflected back, and at the level of about 25%. So you're losing basically 25% of laser energy. You're not coupling 25% of laser energy. If you get rid of the gas, then you're coupling more laser energy into the hohlraum. So it's more efficient for the same energy. You can reach higher radiative temperature. But to do that, you needed shorter pulse shape, which were allowed by high density carbon ablators. So that worked fine. And there are also, we could control better the symmetry of the implosion, and the yield went from 25 kilojoule to 55 kilojoule. And that took about 3 years. And in pressure, we went from 200 gigabar to 250 gigabar at temperature of about 4 K. The temperature is about the same. Yeah, sorry. And then, so as I said, you have 1.3 megajoule of X-rays that are coupled to the capsule, that are coupled to the hohlraum, that are made into the hohlraum. But you're only converting 150 kilojoule. Only 150 kilojoule of those X-rays are absorbed by the capsule, and that's just set by the surface, the size of the capsule. So then the idea was like, can we use larger capsule to couple more energy into the capsule? Well, that was not easy. So that was what was tried for 2 years on, it's called hybrid E. So the goal was increased coupling, and that was difficult because we were expecting the laser to deliver more energy. So going from 1.8 megajoule to 2.1 megajoule. So then you can reach high enough velocity to make enough yield, but the laser couldn't deliver 2.1 megajoule. We tried, it broke many mirrors. So we got stuck at 1.8 megajoule, which means the implosion velocity was below 350 kilometers per second, which was not enough to reach the temperature we needed. So that's why that campaign for 2 years got stuck, because we couldn't reach the velocity we needed. But in 2019 and 20 and 21, Livermore came back to slightly smaller hohlraum. And then if you come back to a smaller hohlraum, the issue, the smaller hohlraum allows you for the same laser energy to reach a higher radiative temperature and a higher velocity. But then the symmetry of the implosion is harder to control. But then we used the trick we used back in 2010, which is laser plasma, which is called cross-beam energy transfer. Basically, at the entrance of the hohlraum, you will have the laser beams overlapping, creating a grating. And the grating will allow you to transfer energy from the outer beams to the inner beams and to control the symmetry, to control where you want to deposit the energy into your hohlraum. So we knew it was working well back in 2010, but we had a hard time simulating the dynamic of that cross-beam energy transfer. We used that back in 2020 in a more controlled way. I will spare you the details, and that allowed us to achieve a much better implosion, better controlled implosion. So that allows to reach 170 kilojoule. Why is it important, 170 kilojoule? Because you are in the burning plasma regime, which I will describe later. And here you're reaching 250 kilojoule. The pressure didn't go up, but you're getting closer to the ignition. And then finally, using the same platform, but a better target, which I explained, the last shot went up to 1.35 megajoule. It's not ignition. Ignition is defined as the same amount of neutron energy than the laser energy put into the system. And here that shot was made with 1.9 megajoule of laser, but you're getting really close from ignition. So the target gain, so here the capsule was larger. So we went from 150 kilojoule absorbed by the capsule to 230 kilojoule absorbed by the capsule. And the target gain is about 0.7. So why did we see that, what caused that dramatic increase in yield performance? Oh, sorry. So as I said, first, better symmetry of the capsule compression. Cross-beam energy transfer that we have used early on the National Ignition Facility was used, this time in a low gas field with lower amount of backscatter, and that allowed us to control the symmetry. Increased coupling energy by 14% just because of the size of the capsule. Increased capsule velocity, and the yield goes up as the implosion velocity to the 4. So if you increase the velocity, and if you don't have hydro instabilities, the yield should go by rather quickly. So by reducing the hohlraum size from previous shot, you increase the radiative temperature, you increase the yield. And importantly, better control of mixed sources, which is smaller field tube and capsule quality. And I explain you that here. So during the years, only several sources of mix have been plaguing HDC implosion. And one of them is the field tube. So here what you see on the left is a picture of the capsule. It's a diamond capsule. And you see that small SI, so it's a small capillary. It's initially it's 10 micron in diameter, and it's made of SiO2. And here you have an X-ray radiograph of the capsule where you see, so it's quite interesting. So the capsule is doped, okay? So you have pure diamond, and then you have diamond doped with tungsten. The tungsten is here to prevent X-rays, M-band, what we call M-band X-rays. So X-ray in gold, it's from 1 to 2.5 keV. To go and preheat the cryogenic ice inside the capsule. So that's a shield to prevent X-rays from preheating the ice. So that's why it's darker on the radiograph, because it's opaque to X-rays. That's what it's designed for, and it's made of tungsten. And you see that small capillary. And in the center of the view graph, what you see are X-ray images of the hotspot taken at different time of the implosion, okay? So you see the limb, you see the hotspot getting smaller, so at 6.8 nanoseconds, it is larger than at 7.2 nanoseconds because it's converging fast. And it's brighter on the limb, well, it's limb brightening effect, okay? It's just limb brightening. But what I want you to look at is that bright spot on the right side of the image. And the bright spot is the jet induced by the field tube. And what you're going to see as a function of time is that bright spot jetting into the hotspot. Remember, this is highly cold matter. So this is a giant ice cube that is emitting a lot of light. So you're losing by thermal conduction because it's cold, and you're using because it's hazy by radiation loss, okay? And so we saw that on many shots, it was clear. So one thing people are good at in Livermore is they have great engineers, but it took 2 years. So we went from a 10 micron diameter to a 5 micron diameter capsule. We even used a 2 micron diameter capillary. And what it did, so those are X-ray images on the right side of the view graph, 170821, 170601. It's two shots where you have an image of the hotspot where you have a 10 micron above and a 5 micron below. And you see that yellow blob, it's much smaller when you have the 5 than the 10 micron. What does it mean? Is that the cooling region induced by that jet of matter is much larger. So you have a larger ice cubes, your temperature is lower, and you're not making as many neutrons. And we saw an increase. It's exactly the same shots. We saw an increase of 30% in yield. And actually, a lot of work was done to understand this effect. Here, what I show you are hydro simulation of the jet impact on the hotspots. So you have density. So it's three. So on the left, you have three images at various times: 5.5, 6.5, 7.5 ns. It's close to bang time, where the neutrons are made. And what you see is the evolution of the jet spreading into the hotspot. So what you see in dark blue is the ablator, and light blue to the left side of the dark blue is the hotspot. And you see that jet forming and launching material, which here is going to be doped diamond or cold DT into the hot DT. And here, if you look at the image on the right side, where you have density and temperature, where you can clearly see that most of the hotspots is at 6 keV, but where the jet is, the temperature goes down to 4 keV. So it really acts as an ice cube, preventing the heat wave to propagate and cooling down the hotspot. But once we understood that, we talked with the engineers, and they went up with a smaller capillary. So we're not, as I said, there are many diagnostics underneath, and yield is not the only signature of ignition. Actually, many of the key experimental measurements point to the 1.3 megajoule shot being in a fundamentally new regime. So typically, if you take the graph on the left, which is yield as a function of temperature, well, you can see when we were below 200 kilojoules, sorry, the temperature was from 5 to 6 keV, and it jumped to 10 keV when you're reaching 1.3 megajoule. And again, this is because your alpha particles, the hotspot is dense enough that your 3.5 MeV alpha particles are going to heat up the hotspot. That's because the kinetic energy into the capsule is the same, but your alpha particles are doing their job and heating up the hotspot, okay? Now, and which is also what, if you look at the second plot, which is the infer hotspot mass and energy, where it's the same thing. You can see that the hotspot mass jumped on that shot to above 60 micrograms, which is why you're stopping out those alphas, because you have a much denser hotspot. The other interesting thing is that simulations are telling you that your emission should be much shorter if you reach ignition. And why is that? Because so imagine you have a Gaussian pulse, and what you do, and typically the full width have maximum of your Gaussian pulse was about 150 picoseconds for years and years and years. Nothing could change it. Suddenly, you take the maximum of your Gaussian and you take it and you spread it. And that's going to narrow down your full width of maximum. And that's what happened, okay? You're going from 50 kilojoule to 1.3 megajoule. Yes, your burn width is shorter, but because your Gaussian gets narrower. And that's what the code is telling you, and that's what we saw in experiment. Yeah, so far we've looked at time integrated quantities, but ICF implosions are very dynamic. So let's look at the time-dependent power balance into your hotspot. So remember, so what you put, so this is the derivative of the internal energy, the EHS, and then you have the PDV work, which is the work you do on the capsule, and you gain energy because your alpha are depositing energy into the hotspot. But you're also losing energy because of radiation losses, just light emitted by the hotspot, and electron conduction. Okay, so we can compute all of those. What I'm going to show you next are results of 1D simulation of the hotspot condition going in. So the hotspot is compressed, that's the heating part, and then it's decompressing. When the shock is reaching 0, it's rebounding, and it's the cooling part. And what is interesting, and we're going to look at 3 classes of shot: 55 kilojoule, 170 kilojoule, and a 1.3 megajoule. This is the PDV work. So the mechanical work, it's for a 55 kilojoule implosion. The 0 is the minimum PDV. Then you look at the alpha deposition, conduction, and radiation loss. And importantly, importantly, what happened is if I take, so let's define now the Q loss on, which is going to be the energy deposited by the alpha minus the radiation loss minus the conduction term. Why is that important? If your Q loss on is positive, you're gaining energy. Okay, if your Q loss on is negative, the radiation loss and the conduction loss are too high and you cannot reach ignition. At 50 kilojoule, obviously you're not close to ignition, your Q loss on is too low because your radiation, because your alpha do not deposit enough energy to compensate for the losses. Now, if you go to 170 kilojoule, it's a different story because the alpha deposition is much higher. That's the red curve, and the conduction and radiation loss are quite the same. So now you start to be in a region where your Q loss is positive, and that's the burning plasma. That's the definition of the burning plasma. The energy deposited by the alpha is higher than the losses due to radiation and conduction. And now, if you look at the last shot, where obviously, sorry, I went back, the energy deposited by the alpha is even higher, so your Q loss is much higher. It's much more positive than before. So, which means that you're gaining energy faster than at a rate faster than what you're losing energy. So that's why you have ignition, and that's why you have a burning plasma. Because you're gaining energy faster than you're losing it. So that's the key. That's why the shots are fundamentally different from what they have been before. So that's the burning plasma. That's what was achieved in the last few months. Oops, sorry. But the interesting thing is you can make simulation, but you can also see it experimentally. And here what you see are 2D images of the hotspot close to bang time. So bang time is when you make ignition, okay? When you make the most of the neutrons, sorry. And I was telling you, the hotspot is getting smaller and smaller. And here what is interesting is that suddenly it's getting much bigger. So if you look at bang time minus 20 picosecond and bang time plus 20 picosecond, here your hotspot is much bigger. Why is it much bigger? Because you have that thermal wave that is propagating into the hotspot and starting to burn out the core DT. That's what you see glowing on your image. Is the burn DT where the thermal wave has been propagating. It's the first time. Typically, it was always getting smaller because it was cooling down. And here, suddenly, it gets much hotter, it gets larger, And that's the proof that your burning wave is propagating. Okay, and that's experimental. It's just an image of the hotspot close to Bangtan. So that's the beauty of it. Yes. So just going to conclude on that, and I will talk a little bit about alternative schemes. So it's been 50 years that the first paper by Nichols was 72, I think. So it took 50 years to get there. Which is longer, not longer, I don't know. Current implosion appear to be right at the ignition cliff. There are still some degradation mechanisms that are here that are preventing robust ignition and going into the megajoule yield. 1.35 megajoule represents only 2% of burnup fraction of the yield, so you can do better. We just need to understand why we don't do better. And that's going to be one of the goals of the future experiments on the National Ignition Facility. So now I want to spend a few minutes on what happened outside of NIF in Europe and somewhere else. So here I only talked about indirect drive, sorry, because that's what I worked on. So, but there is a large direct drive effort carried out mostly at Omega LLE. And here, so why is direct drive appealing? Because I was telling you, you use 1.9 megajoule and you have 1.3 megajoule of X-rays, but then on the capsule, you have only 150 kilojoule. So it's not really efficient in terms of coupling to the capsule. And if you think about an IFE power plant, you can imagine that having a small cylinder of gold or depleted uranium that you want to align at 10 Hertz, it's going to be complicated. So probably an IFE would be a direct drive. But there are some other issues like laser plasma instabilities, which are probably a larger issue in indirect drive. And today we can only go so far on NIF on LMG because they are not optimized for direct drive, the settings of the lasers. But it's making progress. LLE is working really hard on it. It's making progress. They just need to do a full-scale experiments, which today they can't do. There are also a few alternative schemes using which are called fast ignition. Here, the concept is to decouple the compression from heating, which means you don't need to go as fast, and the implosions are much more stable, and possibly you can go to higher gain. So there were two schemes that have been proposed through the years. One using hot electrons. So you use a short pulse that is going to accelerate electrons to MEVs. They're going to release their deposit their energy into the hotspot, and you can use electrons or protons. In Japan, people are working quite a bit on the electron schemes, and in Europe, in Germany, there is one startup which is actually working on the proton scheme. The other and the last scheme I'm going to talk about is the shock ignition. So here you go with direct drive also. And again, the goal is always to decouple the heating part from the compressing part. And here you don't have electrons or protons, but at the end of the compression pulse, which is called P main, you launch a really strong shock. That strong shock is going to heat up. So what does the P main, to P main, you just assemble the density you need, okay? And then you launch a really strong shock that is going to heat up the assembled density. This is, there has been a few experiments. There are some issue about, it's not maybe not as mature as the other schemes. There has been experiments looking mostly at LPI, can you really reach the pressure you need in the strong shock to heat up to temperature you want? That's one of the questions. Yeah, so that's the main question. There are some thought about using not cryogenic layers, but liquid foams that are promising and maybe easier to use. So people are working on that in Bordeaux and at Rochester also. Yeah, oh, sorry. Oh, what did I do? So yeah, so that's kind of the status of where we are and where the, and what is also interesting is that now you have a few startups that is starting to work on IFE project. So as I said, one using the proton fast ignition, and the other one using a different scheme that is a nanitronic fusion reaction, which is proton boron doing only alphas. So there is a lot going on, and it's a great time to work on fusion, I think.